Okay, Algebra 2, we're doing lesson 11, the special role of 0 in factoring. Opening exercise. So for each equation, list some possible values for x and y. If xy equals 10, that's x times y equals 10, you can have, we do this every day, don't we? 2 times 5 equals 10, 1 times 10 equals 10, etc. When xy equals 1, our options are 1 times 1 equals 1, and that's it. When xy equals -1, you can do -1 times 1, or 1 times -1. I can go back here to 10 and say 5 times 2 equals 10, or 10 times 1 equals 10. Not many options. With 0, I can do 0 times any number equals 0, or any number times 0 equals 0. What does one equation tell you? Does one equation tell you more information than others? Really, I think this one is pretty interesting. Okay, it doesn't matter what that number is. Anything times 0 is 0. Okay, so for your opening exercise, find all solutions to the equation x squared plus 5x plus 6 times x squared minus 3x minus 4 equals 0. I'm going to factor this first. Remember, factoring breaks it into 2 sets of parentheses times 2 sets of parentheses equals 0. And we look for factors of 5 that add to 6. We can go through some skills about factoring at another time, but this won't be too bad if I help you out. So this first one, if I have x plus 2 times x plus 3, if I FOIL that, I would get x squared plus 2x plus 3x plus 6, which does equal the original polynomial. And then for the second polynomial, I have x minus 4 times x plus 1. And if I FOILed that, I would get x squared plus x minus 4x minus 4, which does give us the original. Okay, the instructions say find all the solutions. Oh, this is equal to 0. When you have an equation is always equal to 0. So we find solutions. If this 0 weren't there, we would just simplify something, or multiply it and simplify it. But when we have equal to 0, we're trying to find all the solutions. So what we do here is take each binomial and set it equal to 0. And we solve. So x can equal -2, x can equal -3, x can equal 4, and x can equal 1. So our solutions are really all of these things. -2, -3, 4, and 1. Okay, that means that I can put any one of those solutions into the original equation and it would be true. So let's try -2. Let's just try to put -2 in there. So, excuse me, I'm putting, oh goodness, x equals -2 into this whole equation. -2 squared is 4. -2 times 5 is -10, plus 6. And -2 squared is 4. -2 times -3 is plus. -2 times -3 is plus 6, and minus 4. So I have 4 minus 10 is -6, plus 6 is 0. 4 plus 6 is 10, minus 4 is 6. And we learned that anything times a number, 0 times any number is always going to be 0. That's what we said in the previous slide. 0 times any number will always be 0. Cool. So if you put any one of these solutions into the original equation, you would get one of the polynomials being 0. right here. That should be -1. Haha. All right, why is that? Okay, why are these numbers also solutions to the original equation? I just showed you when we put in x equals -2, I have two sets of polynomials equal to 0. I just need one or the other to turn into a 0 for the whole expression to be equal to 0. Okay? We can also say that when we factored the two polynomials, we got all of these binomials. These binomials are equivalent. Equivalent, that's awful. Equivalent to the two polynomials. So those are equivalent. So when we solved each separate polynomial and found what the zeros were, we found that, for x equals -2, for -3, for +4, and for -1, we're going to get 0 for the equation. Cool. I need to point out one of my mistakes. I'm going back a slide. All right, so let's study the solutions to the two separate equations separately. So we're just breaking this thing down into itty-bitty little parts. You may already understand and want to move on, but we're going to break it down a little bit. So the solutions to x squared plus 5x plus 6 are, x plus, say the solutions. I don't need to write out the whole thing. We had the solutions of -2 and -3. Solutions to the other polynomial were 4 and -1. Relate the solutions of the equation x squared plus 5x plus 6 times x squared minus 3x minus 4 equals 0 to the solutions of the compound statement. The one polynomial equals 0 or the other polynomial equals 0. This is the product of. Here we're going to do an or statement. So the solutions, they are the same. The solutions that we get from the product here or the separate ones here are the same. Okay, given two polynomial functions p and q of any degree, and if you remember, this is the degree, the solution set of the equations p of x times q of x equals 0 is the union of the solution set of p of x equals 0 and the solution set of q of x equals 0. So p of x times q of x equals 0. We'll get our solutions there. It's really the union of p of x equals 0 and q, that should be a q, of x equals 0. If a product of two numbers is 0, then at least one of the numbers is 0. Yep, that's what we did in the beginning. xy equals 0. I can do any number times 0 equals 0, or 0 times any number equals 0. Remember, given any two polynomial functions p and q, the set of solutions to the equation p of x times q of x equals 0 can be found by solving each separately and then combining the solutions into one set. And that's what we did. So let's try a few. That was a really long beginning, wasn't it? Find the solutions of this whole equation. And we just said that I can separate them. And it might be easier. So I'll have x plus 3, x minus 3 equals 0. And you do not have to show every single step here. So x equals -3 and x equals 3. Let's try this one. x plus 4, x minus 4 equals 0, x plus 4 equals 0, x minus 4 equals 0. So x equals negative 4, x equals positive 4. I'm going to combine all of those solutions, negative 3, negative 4, 3, and 4. Okay, that's the solution set to the entire thing. Suppose we know that the polynomial equation 4x cubed minus 12x squared plus 3x plus 5 equals 0 has 3 real solutions, and that one of the factors of 4x cubed minus 12x squared plus 3x plus 5 is x minus 1. How can we find all 3 solutions to the given equation? Okay, not too bad. We need to use our division skills. So what we just said was this is one of the 3 factors of this polynomial. So we need to figure out what the other 2 are. 4x cubed minus 12x squared plus 3x plus 5 over x minus 1 equals. Okay, I'm going to skip that step because I don't need to reteach you how to divide. You guys remember how to divide. So I know that if I do that division, I would get this polynomial. So now I know that 4x cubed minus 12x squared plus 3x plus 5 is equal to x minus 1 times 4x squared minus 8x minus 5. Okay? I need to factor this trinomial. It factors into 2x plus 1 and 2x minus 5 and x plus 1. I take, oh, that's too many parentheses. There we go. I'm going to take each one of those binomials, and that's my solution. Set it equal to 0, and then solve for x. Set it equal to 0, and then solve for x. Sorry for the distraction in the background. That would be the epic Lego wall. Then I have x equals positive 5 halves. So my solutions are negative 1 half, negative 1, and positive 5 halves. Cool. Okay, a discussion here. Okay, we just said that the previous equation, which was really long, has 3 zeros, which are right here. If you grabbed your calculator and you typed y equals 4x cubed minus 12x squared plus 3x plus 5, your graph would look like this. The first thing I want to point out to you is I have a degree of 3. That means I'm going to have 3 solutions. Okay, that means that my graph will cross the x-axis 3 places. And we have 1, 2, 3. As we solved our equation, we found where x equals negative 1 half, where x equals 1, and x equals 5 halves. And you see that's where we cross the x-axis on our graph. And that's not a mistake. That happens every time. That's sort of the definition of solutions and zeros. It's where y equals 0, what is x? It's the x-intercept of the graph. So consider the polynomial functions given, p of x, q of x, and r of x. Because p of 2, so you take your equation p of x and evaluate it at 2 equals 0, q of 2 equals 0, and r of 2 equals 0. The number 2 is a 0 of p, q, and r. Okay? Negative 3 is also 0 of p, q, and r. Even though these polynomial functions have the same zeros, they are not the same function. They do not even have the same degree. P of q has 2. Let's see, that has 2. They're all of the same degree, but we have two solutions of -3 and 2, two solutions, -3 and 2, -3 and 2. They all have the same solution, but when you graph them, they're not even the same graph. Okay? They may not be the same degree, because if you found the original polynomial, some of these solutions may be duplicates, which we'll talk about here in a minute. You might have x equals -3, a duplicity t of 2. So that might be a solution twice, etc. But we'll get into that in a minute. Multiplicity. Awesome. All right, we would like to be able to distinguish between the zeros of these two polynomial functions. If we write out all the factors for p, q, and r, we see that for p of x, okay, that's our totally factored out. So we have our solutions of 2, -3, and -3. So -3 actually occurs twice. For q of x, we have -2, -2, 3, 3. I did that backwards. Let's erase that before you guys are all eating candy tomorrow. We have 2, 2, and then 4 -3s. So see the duplicity. Q of x, the graph is actually 1, 2, 3, 4, 5, 6. It's a degree of 6. So our original would have x to the 6th in it, our original equation, which is why the graph looks different than p of x, because p of x has a degree of 3, and r of x has a degree of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 2 written 1, 2, 3, 4 times, and -3 written 1, 2, 3, 4, 5 times. That's a lot. So we notice that x minus 2 is a factor of p once, and x plus 3 is a factor of p twice. We say that 2 is a 0 of p with a multiplicity of 1, and -3 is a 0 of p with a multiplicity of 2. I got that wrong on the last page. Hold on. Zeros with multiplicity of 1 are usually just referred to as zeros. We don't usually say multiplicity of 1. We only say multiplicity when it's a higher number. Okay, so we have q of x equals that and r of x equals that. What are the zeros of q with their multiplicities? So I have, oh goodness, sorry, 2 with a multiplicity of 2, and -3 with a multiplicity of 1, 2, 3, 4. Okay, r, I have 2 with a multiplicity of 1, 2, 3, 4, and -3 with a multiplicity of 1, 2, 3, 4, 5. Can you look at the factored form of a polynomial equation and identify the zeros with their multiplicities? Yes, when it's factored, you're good to go. You can find everything that you need. Can multiplicity be negative? No. Okay, it's either a multiplicity of 0. No, I'm sorry. It can't be 0. It can't be negative. It can't be a fraction. Your zeros happen once or more. Okay, if it's 0, that means that that 0, that x equals whatever, doesn't occur. So why list it? Okay, if it's a fraction, that means it happens a fraction of the time. No, that doesn't. Okay, your multiplicities have to happen full, like integer numbers, positive. Your answer, like x can be equal to a fraction, but it has to have a multiplicity of 1 or greater. Okay, exercises 2 through 5. Okay, go ahead and try this one on your own and see what happens. I'm going to push pause. All right, there you go. Notice, one thing I'm going to point out, you can look at everything else. Square root of -1 is not a solution because it's not a real number. We're going to get into imaginary numbers, which are real things, and but it's not a real number. Okay, these two, I'm pushing pause. All right, there we go. We have C and D. Let me know tomorrow if anything doesn't make sense. All right, find a polynomial function that has the following zeros and multiplicities. What is the degree of your polynomial? Okay, really quick, if I have a 0 of 2, oh, sorry, again, that means that x equals 2. So if I backwards that, not a real word, I know. It means I have x minus 2 equals 0. So we have, I don't know, p of x, just to name it, x minus 2 to the multiplicity of 3. Then I have x plus 4 to the multiplicity of 1. I don't have to write the 1 though. Then I have x minus 6 to the multiplicity of 6 and x plus 8 to the multiplicity of 10. Okay, what is our degree? 10 plus 6 is 16, plus 1 is 17, plus 3 is 20. Awesome. Is there more than one polynomial function that has the same zeros and multiplicities as the one you found in exercise 3? Yeah, there could be. If we think back to the last problem, one of the binomials we had was x squared plus 1, which gave us x equals the square root of negative 1, not a real solution, so we didn't count it in our solutions. So I could take that long equation and put any random, not real number in front of it, and that would be the same solutions and multiplicities, but not the same equation. I'm getting all these in here. Okay, so actually we can make this a different letter. Okay, P of x and Q of x are not the same, but they have the same solutions. Okay, can you find a rule that relates the multiplicities of the zeros to the degree of the polynomial function? Okay, if you remember we had, oh for goodness sakes, P of x had a degree of 20, and 20 solutions. Degree of 20, 20 solutions with multiplicities, right? And then we had Q of x, which our degree was higher because we had that x squared plus 5 in the beginning, and we have to count that. So the degree is 22, but we still only had 20 solutions. That's my example. So if P is a polynomial with degree n, then the sum of the multiplicities and the sum of all of the multiplicities of the zero is less than or equal to n. Okay? So the solutions have to be less than or equal to n. So this is a degree of 22. The number of solutions is less than the degree. Degree of 20, 20 solutions equal to. In closing, part of the lesson today has been that given two polynomials, p and q, we can determine the solutions to pq equals 0 by solving for both p and q, even if they are high degree polynomials. If p and q are polynomial functions that do not have any real number zeros, do you think the equation p times q equals 0 still has real number solutions? Can you give an example of two such functions? So what it's saying here if p of x doesn't equal 0, and q of x doesn't have any, if p of x doesn't have any real solutions, and q of x doesn't have any real solutions, then there's no possible way this can't exist. Okay, one of them has to be 0. So an example would be p of x equals x squared plus 1, which we've already said has no real solutions, and q of x is x to the 4th plus 1. If I look at this one, I'd have x to the 4th equals -1. Okay, 4th root of, it's not real. I can't take the square root of a negative number. Okay, so that would be your example. P of x doesn't have any real solutions, q of x doesn't have any real solutions, so p of x times q of x won't have any real solutions. Okay, there's your relevant vocabulary. Just make sure you know them all in your notes. Page 2, lots of them, right? Okay, so please read through them. They're very, very important.